Okay, good evening everybody. I hope everybody's having a wonderful day. So just to give everybody a heads up for anybody that's just coming on in, I'll be posting assignment 4 either tonight or early tomorrow morning, okay? So it'll involve hashing, you'll get to implement some elementary operations of a dictionary, and you also get to implement part of quicksort. So it's going to be a fun time. Looking forward to showing it to you. So anyways, last day I started talking about open addressing. So we've been talking about hashing the last little while. And one vital problem that we run into with hashing is how we resolve collisions. So at first we had with separate chaining, right? The goal here was, okay, whenever I run a collision, I'm just going to maintain a bunch of linked lists. And I just simply use the linked list to store another node that stores the record that I want to hang on to whenever a collision happens. So all my solution is just to use more memory. This is in contrast to open addressing, where I'm actually going to I'm going to directly place my entries into the table. And the idea with how I'm going to resolve collisions is I use this idea that we talked about called a probing sequence. So the idea, you think of it like me as Professor Bunny, I hop to the next available spot for which I might be doing my search, I might be doing an insertion, or I might be potentially trying to find a specific key. So I thought we would do an example of how we would do insertions into a hash table using this linear probing approach. Sorry, I'm getting very excited here. So recall, in linear probing, the probing sequence works as follows. So I'll address that in a moment. So recall that in linear probing, the idea is that I attempt to search at that position. Then if I don't find it there, or I can't insert there, I will then go from wherever h of k takes me. I'm going to increment it by 1. So I check out h of k plus 1 mod capital M. Remember, capital M is the size of the table. If there's nothing I could do there, I just hop over to the next spot. I hop, and I check the next spot for what I'm trying to do. If I'm trying to search, do I find it there? Do I not find it there? If I don't find it there, I'm going to do another hop until I either find it, or say, for example, I'm doing an insertion, I'm trying to find a spot where I could fit it in. But the whole idea here is that the table might get full. And if that happens, you're going to have to probably rehash the entire table, which is the process of simply creating another array that's larger based on some of the ideas we've talked about before about array resizing. And instead, what you'd have to do is you'd have to apply the hash function to every one of your records and reinsert these into the larger array, and then that becomes your new hash table. But that's very expensive to do because I have to do it over the entire table. So there was a question about what if the size is full? How are we going to store the data? So this is one thing that's about open addressing is I'm using the table directly. So if it becomes full, I have to rehash the whole table. So usually when you're using this approach, you have to keep in mind the size of the table based on how big you think the table might need to be. So this would be something of a practical consideration, that you figure out how big does my table need to be and what's an appropriate size for the table. So these are things that we've been talking about already. For example, with separate chaining, we talked about the idea of a load factor, and we used this idea of load factor to help us learn about separate chaining and how maybe we might design the table. So for example, on your next assignment, I'll be asking you to make it so that the size of the table matches so that it fits a certain load factor. So I'll talk all about which one is more appropriate for certain load factors towards the end of this discussion today. So I'll be touching upon that in a wee bit, okay? So I thought I would go through an example of us doing some put operations on some records in the manner that we use for linear probing. So I thought it'd be important that we kind of see some good examples of doing this. So I'm going to go through each one of these records, and I'm going to put them into my hash table here. This hash table has size 9. And all I'm going to do now is I'm going to be applying this hash function. So the first thing I'm going to do is I'm going to consider this record, the one with key 18. That's going to be placed because of 18 mod 9. That is 0. I'm going to place that in position 0. Then, next, what I'm going to do is I have 16 mod 9. This is the next one I'm going to now put into the table. So I'm going to consider this one here. I'm going to do a put operation. So can somebody tell me what's 16 mod 9? What's 16 mod 9? It's 7. Very good, very good. So it's 6. So it goes to the position 7. Okay. Now I am going to next consider 8. So this one's really easy because 8 mod 9 is just 8, right? So I'm just going to place that one in here. So you see, it's very straightforward. I just place it in if there's a spot for it available. I must stress that this table is full of a bunch of null references or just null in them. So I'm just not writing them down for the purposes of time. So anyways, when I do this next, so now I've done 8, let's do 44. So let's think about 44 mod 9. Now, the one thing I like to think about are multiples of 9. So if I were to have, for example, 5 times 9, what's 5 times 9? Yeah, it's 45, but this is 44. So you know right away that we're going to have to be a bit careful about this, because notice that 44 mod 9 is in fact going to be right here. It's going to be 8. So 44 mod 9 is equal to 8. So we have a collision. So there's a collision that happens. So there's a collision. So now this is where I'm going to need to pull out the probing sequence. And now remember, in linear probing, what I do is I take whatever position I have gotten from my hash function. I'm going to add 1 to it first. I take mod m to that, in this case mod 9. And then I try the next position and see if I can use that one. So 8 plus 1 mod 9, that is 9 mod 9, right? So that is just simply 0. So what does that mean? I'm going to try to put it right here. Can I put it right here? No, right? It's already occupied. It's already occupied. There's no squishing our friends like Squish-a-Chew over here. There's none of that gonna happen here. So I'm going to apply the probing sequence again. So instead of it being 8 plus 1, I go 8 plus 2 mod 9. So 8 plus 2 mod 9, that gets me a position right here. So I'm making a hop. I hop all the way back up here. I hop, and then I find this spot is available. So all I'm doing is I'm making these little hops like I'm a bunny rabbit. And I try each one until I find a spot I can put it in. But notice as I'm doing this, by the way, when I'm going through this probing sequence, if I don't find my spot right away, it may be somewhere along my journey through these hops. Because remember, if it, say for example, has the exact same key, it had to have gone through the same set of hops at some point. So question, how or why did we do the +1 or +2? That's the probing sequence from last day, right? So if you're curious about what exactly I'm doing here, it's actually this algorithm right here, but I'm going to talk about this in a moment. So remember, if I can't insert in the spot I'm at, I apply the probing sequence. The probing sequence says, first I try my spot. If I can't put it there, I try the next position. If I can't put it there, I try the next position. If I can't put it there, I try the next position. And so on and so on. It's either I'm going to find a spot or I'm going to examine this whole table, or there's another third possibility. When we do insertions, remember we're dealing with a dictionary. Dictionaries have unique keys in them, right? So we might run into a duplicate key. So that's something we have to keep in mind, because remember, when I have two keys that have the same value, they're going to hash to the same position, which means that when I do this probing sequence, I'm going to run into it if it already exists, which is a nice feature, by the way. But let's keep going here. Let's keep going here. So I've got 44. Next, just do 3. 3 is really easy. 3 mod 9 is just 3. So I'm just going to place it right here. Okay, now we got 1. So a key with 1 in it. So I got a 1. So notice here, I can't place it right here because 44 is right there right now. So what position in the table should I place it in? So it doesn't go into 1. So I continue through yes, exactly. I go to position 2. And now, I see an interesting question, but there will be no duplicate key, right? So in our example, there isn't duplicate keys, but I must stress that the process we're going through, because we have to go through our hops to find the first available spot, in this case, one with null in it. If this happens, we would have to have hopped by the key if it's the same as ours. So that's actually a way we can check for duplicate keys. So we would not insert it if it's a duplicate. We would report an error happened. So lastly, we have 19. We have 19. So 19 mod 9. What's 19 mod 9? So I like to think about it in terms of multiples of 9. So I have 9, 18, then 27, but notice 19 is not as big as 27. It's one higher than 18. So you know, since 18 is a multiple of 9, 19 has to be one higher, right? So that means 19 mod 9, that's just going to go into position 1, right? It's going to go right here. But we're in a little bit of a doozy here, right? Notice that I can't put it here, so I'm going to do a hop. I try this one. Now, there's something there. There's something there. I'm going to keep hopping. Remember, think of me as the bunny rabbit. So I'm just going to hop, 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 hop until I get the 4. Exactly. Exactly. So I just place 19 here with V7. Very good. Very good. So that's how you would just do insertions with open addressing, in particular with using linear probing. So now I want to walk you through the process of this, because we've seen some examples of how you would carry this out. And like I said, just think of me hopping like a bunny rabbit. Just hop, hop, hop. I go through each one doing hops. So for the put operation, I just simply follow the probing sequence, inserting the record in the first available slot of T. That is null, right? This assumes it fits in the table. Error is returned if a duplicate key is encountered or all of T is checked. Because if I encounter, remember, you don't want me hopping around this table for hours upon hours upon hours on end, right? We need to stop this process, just like when we talk about the get operation. There's got to be a point where you got to let your professor off a little bit, okay? This hopping business, it can be quite exhausting after a long time. It's a good workout, though. It's a good workout. It's good for the calves. So, anyway, so here's some pseudocode for this. So I have put, I have input being key, and I have data. The output, it adds a record, error otherwise. So I'm assuming it's adding it correctly. I've just abbreviated this because of space. So first thing I always do is I apply the hash function to tell me what position I should be starting at. And then I have this counter variable just like in my get algorithm that I gave you last day. So every time I examine a position, I'm just going to increment this counter. And if it equals m, then I had to have looked through the entire table. So I have a while loop, and I keep looking for a spot where it's going to be equal to null. So if it's not null, then I check if it's a duplicate, right? Remember, like I said, I might hop right by the duplicate key if it happens. So if that happens, then I'm just going to report an error. Now, you might ask, Dan, what does that mean? Remember last day I talked about how this would be natural for us to use an exception. So you would throw an exception here. So this is a very natural way where you could put an exception for like a duplicate key, for example, to be reported. Then, if this doesn't happen, obviously, if this was satisfied, you would just stop right here, because if you threw an error like this, then you're done, right? You're not going to do anything further. So if that doesn't get satisfied, I'm going to increment the position by the probing sequence. It says to increment position by 1. I mod m that. And then I increment my counter variable. Obviously, I want to make sure that I don't check the whole... If I check the whole table, I want to make sure I've done so. Otherwise, I'm going to hop here for a good while. And if that's the case, I return error because I couldn't put it in. It failed to be inserted because the table's full. And then if I do find a spot where it's null, this condition will become falsified, allowing me to place the record into the spot. So remember, a record is a key value pair, which is why I've indicated it like this. But yeah, so you might ask, Dan, what's the worst case analysis here? It's actually very similar to the one we did for get. So get is also, in worst case, it takes linear time. But on average, it's still big O of 1. So remember, the whole idea here is that if we have the assumptions in play that we're working with, or technical assumptions, then we obtain these really nice average case running times, which is something that gets reflected nicely in practice. I'm not even kidding. It's fast. It's fast, but you're using that memory to do it. So are there any questions before we talk a little bit more about linear probing? Are we all okay with this? Give me 2 thumbs up if we're ready to go. I'm going to talk a little bit about removals, because you'll notice that in separate chaining, removal seems really straightforward because I could just use the hash function. I could just use the hash function to tell me which linked list to follow, and then I could just do the removal right there, right? I could just remove from that linked list. However, we're going to see that there's a technical problem with our setup that makes things... So can you go over the first if statement once again? Sure. This is checking. So t sub pos dot get key. I'm getting the key of the record at that position in the table. If it equals k, because the input for this function is a key value pair. If it equals the key I'm planning to place in, that means there's a duplicate. So if that's the case, I'm going to report an error. That's how I defined it in a dictionary, is that if there's a duplicate, I'm not allowed to put it in. Some people define the dictionary to allow it, the overwriting of this to happen, but we're not going to. We're going to forbid that from happening. But yeah, we're going to see that there's this really interesting technical issue that we're going to have to deal with, because now we're using the table itself to store everything. So let's head on over here. Let's head over here, guys. The camera wanted to just hang out over here. So let's go over here, okay? So we got to be a bit careful about removing things from this dictionary. Well, our hash table. We have to be a bit careful in this case. So you remember, I am the bunny rabbit. I hop to the next available spot. And when I do my insertions, you've seen how I hop over, but I hop one by one through entries in the table until I find a spot that's occupied. So when I want to remove something, I can use that same probing sequence to go through and remove the record. It's actually really nice and straightforward, because I can do a search very similar to what we did with get, to just find it in the table, and I could just simply get rid of it. But there's a problem with that idea. So the first thing I want to point out is, if we assign one of these slots to null when I remove it, we might lose a chain of hops. So just to give you an idea what I mean, so I'll come right back over here, but I wanted to come back to our picture. Do you remember I did a whole bunch of hops towards the end over here, where I did hop, 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 all the way to position 4. So suppose that I had this situation. So suppose that this was a thing that happens, just like in my example over here. So I just want to show you what I mean about this problem that I'm pointing out to you. So suppose that I were to remove, if I applied remove, so if I went remove 3. If I went remove 3, I would apply the hash function. It tells me 3 mod 9. It's right here. If I just turn this into null, so if I make that null, so I take out the data that I want, I make it null, and suppose I come along again and I want to use the get operation. Suppose I want to use it with, say 19. Say I use 19, I go get 19. If I use get 19, what did we do? We started right here, we did a hop, but oh no, this right now is null, right? So now we have we have a problem here. The bunny rabbit has lost its way. We don't know how to get over to 19 anymore because I've eliminated the hop that was necessary to get over there. So I'm going to have to deal with that, and there's a couple different ways I can. So remove is not as pretty as it is, say, with separate chaining. So in this case, I need to do something with this. So let's talk about what we could do. So that's a big problem, right? Like, you can see how that's a big problem. If we don't know where our bunny rabbit's supposed to go, they won't surely be able to find the record I'm looking for, right? Because if you could almost think of it like the bunny remembers where to go based on the hops. So when I go hop, 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 there might be a hole in the ground. That's not good. So I need to find a way to deal with this. So what I'm going to suggest, there's a couple different ways I can do this. The first one is I could just simply rehash the entire table without that record in it. But as I mentioned just a moment ago, that's very expensive to do if you have a large table. I would not advise doing that if you have a very big table, unless you really have the time to spend doing that, which maybe not. You may want to do that. You may not want to do that. That's not my business to say who does what. But here's an idea. Here's an alternative idea that we can do. So you know how I talked about the bunny making the hops? And then I talked about there being a hole in the ground and the bunny falls into the hole? Well, we don't want our bunny to fall in the hole. So instead, what I was going to suggest is that whenever we remove a record, so meaning that we have one of these holes buried, I'm going to pave over that hole, and I'm going to put some marker there to tell me that I deleted something here. Just keep going. So this is the idea of a lazy deletion. Now, sometimes this is used in systems, for example. For example, if you have a cache, for example, sometimes you have it where you mark things for deletion, so that later on when you do the expensive operation of clearing out a cache, for example, you might use this type of strategy. So you might ask, okay, so what does that mean to do a lazy deletion? Well, what I'm going to do is, hey, look, it's Spooky the dog. Everybody say hi to Spooky. Hey, Spook. We're having fun here. I'm watching her, okay? Okay, if Spooky comes by again, I'll make sure I say hi for everybody. So let's see. So anyways, what we're going to do is that in that position, you know where I make the deletion? It's one of those great mysteries. So what I'm going to do is I'm going to set or mark the entry that I was going to, you know how I said that I was going to, Professor Spooky. It's exactly. So anyways, what we're going to do is you know when I put null in my original idea, instead I'm going to mark a spot, and this isn't going to be the same as a key. Instead, it's just going to be something else. It's not going to be null. It's just going to be a label that I'm going to be able to distinguish between a key and this delete marker. So I'm just going to label it as delete, so that if I come across this, I'm just going to treat it like it's just a free spot to hop over, so that I could just retain those hops. So it's just about remembering where we need to go. So I must stress, if we ever need to rehash the table, you could just ignore all of, you could just remove, like you don't even have to consider these deletes. They're just there to help us perform the hops. So you might ask, Dan, what does that mean then? So in the remove operation, here's what I suggest we do. So I'm confused, like why would we stop if null is in the table while searching for the key? So remember, like in the example I showed you there, if I perform a hop, and suppose that my key is the one that is the one directly below where I set null in a previous deletion, I will not be able to know to go to the next one because that spot used to not have null in it. It used to be occupied. And at that time, when I entered that record in the entry just below it, there was something there. So that's why we have to be a little bit creative about doing this. So when we do the remove operation, you just apply the probe sequence just like when we did get and put. You just follow it until you find the key. And then what you do is instead of just setting it to be null, you just mark it for deletion. So you just set a delete tag. So it's just something that's different from a key or null. So it's something that you would just simply just look for that isn't null. And you just place that there if it exists. So if you're able to get rid of the record with key K, you just return the data you want, you mark this as delete. Yeah, we want to make sure, yeah, exactly, that's exactly it. So we're leaving some popcorn on the ground. I love that analogy, that's wonderful, I love that. So it's just like if I left popcorn on the ground to help the bunny find where to go. Just like when I talked about I'm paving over the hole, so I know the bunny can keep hopping along. Exactly, exactly. It's very important in our probing sequence we don't lose track of where the bunny needs to go. Because at some point that bunny used that place to hop. So all we're going to do is if that's the case, we mark for delete. And otherwise, if we don't find it or we examine the whole table, we just report error. Meaning that we failed to do the removal or it just simply was never in the dictionary in the first place or our hash table. So anyways, let me just do, and I just feel like I want to just do one more example with that just to illustrate my point. So let's head back over here. Yeah, so the example with 19 mod 9, that is actually a concrete example. So if I did 19 mod 9, remember, in our example, I like that you're bringing this up because this is the one we were talking about previously. So let's see how we would fix this. So let's see what we would need to do. So if I wanted to attempt, so first I, for example, removed, let's try just doing it with remove 3. In the notes I remove a different key, but either way, 2 examples doesn't hurt, right? So I'm going to first remove 3, and then I'm just going to get on 19. So I'm going to get 19. That means it should return back me V7. So if I do remove 3, instead of just straight up just making this null, I'm going to mark this as delete. And I must stress that keys, so your keys are not equal to the delete tag. But I must stress that they're not null either. So you'll notice that all of our pseudocode relies on it being null or not null. So notice that this is just to ensure that we're not treating delete like null. That's its only purpose. So now if I do get 19, I start right here, right? Then I do my hop. And this isn't 19, right? So I keep going. I hit here, but notice that this it definitely does not equal my key, right? When I do the get operation. So I keep going. I hop again, and there's 19. I found it. So now I fixed the problem. So do you see how by using this lazy deletion, we can actually fix any of these problems? But you're going to notice that this actually has a negative consequence on the table. If, say, for example, I do many deletions in the table. Does anybody have any ideas why that might be a problem? Any ideas of why, if I, for example, it takes up space, exactly. It takes up space. So for example, it could be possible for like almost the entire table to get filled up with deletes, which wastes space. And that's when you naturally might think of maybe rehashing the table. So, wonderful. So I must stress that the analyses for put, get, and remove are all extremely similar. They all have the same time complexities. In the worst case, they take linear time, linear in the number of elements, and then, of course, on average, they take big O of 1. So you're asking, why did we delete 3? So this is just an example. So I performed this operation, and then I did get 19. So this is just an example. So let's see, why null terminates the program. So just can you clarify just your question a little further, just so I could get an idea what you mean by that? Just I want to make sure I can address your question. If in place of delete if you put null, okay. So remember, the whole problem is that if there's null here, we don't know how to get the 19 anymore. That's the problem, is that we lose the ability to use our probing sequence to find things that we used to place in spots. So the whole idea is with lazy deletion, we introduce these markers that mark a deletion to ensure that we can continue hopping along to where we need to go. If we fail at this, that means that if I do a get operation, that means if you go back to the algorithm for get, if I hit null, there's nothing else for me to examine any further. That's how get works. So if I encounter null, there's nothing else there for me to examine. I'm done hopping. So this is just to complete that picture, is that we're resolving the issue of hops. But yeah, just think about it like the bunny rabbit. We're trying to help the bunny rabbit reach 19. But yeah, no. So I want to pose you a couple of interesting things to keep in mind with linear probing. So believe it or not, that's like linear probing's nice because there's nothing too overly complicated about it. It's just that there's some modular arithmetic using this mod operator. It's not too overly complicated, so it's very easy to implement. So if you have very, very strict memory requirements, it's rather nice to use. So I just want to mention a couple issues with linear probing. And we actually have run into it, but I haven't really said anything about it yet. So there's another question. While searching the key, why can't we do it using the size and go from 0 all the way up? So now remember, that takes away from the purpose of the hash table. The whole point is that I don't want to search the whole table, right? Like you can do that with the table, but that takes away from the goal we're trying to achieve. The goal here is I would like to be able to obtain the record in average time of big O of 1. If I do a linear search over the entire table, that most certainly will not be that on average. It'll be just no different than linear search. So that being said, I want to talk about a couple issues here. So this is the first one. So I must stress that there are some ways to get around these deletes filling up your table. Now in the pseudocode that I have, I don't account for this, but I feel like I want to acknowledge it, is that, you know, when you have these deletes here, assuming that you check for all the duplicates first, so you ensure that there's no duplicate key, you can't always fill up these delete spots with new records on your put operations, assuming that you check for duplicate keys first, right? Because you would not want that to happen where you're just examining and you never check for the duplicate keys, because otherwise you might introduce a duplicate record. Well, a duplicate key for a record, just to be more precise. We cannot remove the deletes except except for put operations, if we assume we check for duplicates first, for duplicate keys first. So that's one way you can remedy this. Our put algorithm does not do this though, just to be very clear. But you can easily modify it so that you use, for example, get first and see if it's already in there. And then you can try the process. So keep in mind, hashing has its benefits generally, but the idea is that I would like to get around the big issues that we ran into for our simpler implementations, where the idea was when I do searches, there's sort of this trade-off that I ran into where if I attempt to search, when I search, I fail. I may have to scan through all the elements. I'm trying to give you a way to try to cut that back by trying to use this idea of hashing. But we use some important assumptions for how we hash into this table to achieve these things. So keep in mind, we can't just remove these out front. You have to be very careful about them. So the table can fill up with deletes. We might need to rehash later. Why? Because the performance degrades. Because if you have to do all these extra hops, they're just sort of phantom elements hiding around in your table. In some technical jargon, some people call these delete tags in the lazy deletion, they call them tombstones. So when you hear like, oh yeah, they're like phantoms, it's sort of a play on the word. So that's one thing you have to be mindful of, is that when you do lots and lots of removals, they can degrade the performance of the table. So you have to be mindful of this. The other issue is actually one that we've exhibited here, but I'm going to talk about it now, is that clusters form. So one thing I want to talk about what this means, what a cluster is. So in hashing, you'll notice that when I tried to get 19 here, I perform a whole bunch of hops, right? I hop from here, I hop, 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 right? Now, as I perform more and more of these insertions, depending on what keys I place in, it's possible for these hops to grow larger and larger. So I have to perform a longer sequence each time of hops. So notice our algorithms rely on hopping one position to the next, one after the other. One after the other. These form clusters that degrade performance. So I'll reiterate what I just wrote here. So clusters form. Notice our algorithms rely on hopping one position to the next, one after the other. These form clusters that degrade the performance. So what do I mean by a cluster? Over here, when I do all these hops, notice that I have to go from here all the way here. So this is an example of a cluster. So these clusters can get quite long. And if you have many positions where you're going to end up getting these clusters, they degrade the performance of the hash table. So just to make sure I hammer this idea in, it's not a very strange idea either, is imagine my friends again. So I have a few of my friends here. I have quite a similar thing going on. Say if I go with my friends to the theater, for example, and I want to go see a movie. Now suppose that I have my one friend here. They sit in the first spot. Now, suppose that both my friends really wanted to sit right here. Well, suppose that I told them, oh yeah, well, you could try asking your friend here to sit there, and your friend's like, nah, man, I took this one first. So my one friend's gonna go right here. Then my one friend here is still really stubborn about wanting to sit in here, so I tell my friend here, hey, ask our friend here to sit there. My friend asks, that's very stubborn, says no. My friend here says, no, I tried doing that, that didn't work. So I'm going to sit right here. So notice that when I do this process, it's no different. It's like this is what a cluster is like. So that's what happens in our operations. So these can form very, very long chains of hops. And those are the things I'm referring to as clusters. They slow down the performance of our operations. If you say, for example, doing a get operation that goes all the way through the table like this. Don't mind the barking. She's just very excited. That's that spooky dog. But yeah, so now naturally, we'd like to know how we can resolve this issue. So how can we resolve this issue? So I'm going to propose one way we can try to alleviate this issue. And it's going to be the final collision resolution technique I'm going to show you. It is actually something called double hashing. So this is one way we can resolve the issue of clusters. So let's talk about double hashing. So let's talk about double hashing. So believe it or not, double hashing is very similar to what we were talking about with linear probing. Just the probing sequence is going to be different. Other than that, our algorithms are all the same. Just the probing sequence changes. So let's talk about double hashing. So double hashing. Sorry, I was a little squeaky. So I'll say we can avoid. So this is one way we can alleviate the clusters. Is imagine instead of having those clusters where they hop one after the other, what if I can try to spread out those hops? So you think of my cute little bunny, where I hop one hop at a time. I go one hop each time, right? Now suppose I gave my bunny rocket-powered boots. So instead of doing these little hops like this, it goes, oh, it takes a big hop. I apologize for anybody's ears that had to hear that. So imagine I have my bunny and I have rocket-powered boots, and instead of making those little hops, I can make big hops. So I can avoid these clusters from occurring. So it's not going to be perfect, but most certainly it's a way that I can try to reduce this clustering. So we can avoid clusters in linear probing. In linear probing using double hashing. So let me define what that is. So once I do that, I'll do an example just to show you what it's all about. Yeah, it's a good time. So you know how we have one hash function, right? So double hashing, as the name suggests, instead of just having one hash function, we're going to have two of them. So here's the idea. Let there be a second hash function. See, a second hash function. And I'm going to call this one h prime of k. So instead of making one hop at a time, we're going to use the secondary hash function to gauge our hops. So instead of incrementing by 1, increment by multiples of another hash function. Another hash function. And this hash function often has a more technical name. So usually we refer to this as the secondary hash function. Secondary hash function h prime of k. So that's what its name is. So often in hashing discussion, if you talk ever about hashing, if you talk about double hashing, you have your primary hash function and you have your secondary one. So we just have the hash function, then you have the secondary one, our secondary hash function. So let me give you what the probing sequence looks like now, based on what I just described here. So instead of just hopping by one, you're going to hop by multiples of this secondary hash function. Sorry, I'm getting very excited here. So the probing sequence, I check h of k first. Then when I fail at that, I try h of k plus h prime of k mod m. If this fails, I'm just going to go h of k plus h prime of k times 2 mod m. And then you'd keep doing this. So if that fails, h of k plus h prime of k times 3. So keep in mind, this is all together for the secondary hash function. So I'm adding this on each time. It's each a multiple of the other hash function. Mod m, and so on. That's what the probing sequence looks like. So instead of it just being plus 1, plus 2, plus 3, the idea is I'm going to have this other hash function that's going to deal with what the offset is going to be, how much I'm going to do these hops. So I'm equipping my bunny with rocket boots instead of just simply little cute one-step hops. So I must stress that means that these hop sizes can be different, and it depends now on the key k. So you might ask, Dan, what would one of these secondary hash functions look like? So I have to tell you about the design of the secondary hash function. So let's head over here. I got to talk a little bit about that. There's a couple of technical things that you need to know. These are all number theoretic reasons why we have to design the secondary hash function the way it is. Some of these things I can't talk so much about in this class, which I would love to talk about it, but we only have so much time, and it's a very fascinating topic in its own right. But some of these things I can talk about, which I'm going to try my best to do that with. So I'm going to talk about some technical remarks about the secondary hash function. So when we design the secondary hash function, it has to satisfy certain properties. So technical requirements, I'll just phrase it this way. So the first one is that actually I'll use numbers. H prime of k can never output 0. Does anybody have any ideas why we cannot have h prime of k spit out a value of 0? Any ideas? Yeah, exactly. 0 times a something, it's still 0, right? We will not move anywhere. The rocket-powered bunny is not landing. It's just going to simply just stay there, just sitting on the ground, sitting and waiting for us, okay? So it's not going to go anywhere. So we must ensure that it never outputs 0. Otherwise, we'll be sometimes giving keys for a secondary hash function where it's just going to simply just sit there doing nothing, which isn't going to accomplish what we did with linear probing at all. All those algorithms relied on me performing some hop, right? All I'm doing now is I'm just making larger hops. But the thing is, these hops are all systematic, right? Just in the same way when I talked about linear probing. So that's one. The other thing is that what we have to talk about is that in double hashing, the table size m must be prime. So it must be a prime number. So this is one of those cases where you really need to have this in place. I'll give you an example to justify why this has to be the case. The third one is I would like to give you an example of an effective secondary hash function that does satisfy these properties. Under the presumption capital M is a prime number. So, an effective H prime of K, keep in mind this is the only one, but this is one that will work perfectly in tow with double hashing, is Q minus K mod Q, where Q less than M is prime. So Q has to be a prime number in this setup, but it's strictly less than M. So what do I mean by the first one? Remember, when I do the probing sequence, I do 1 hop, then 2, then 3, then 4, right? I go 1, then I hop again, then I hop again, right? Each one's an increment of 1. If I had it where it is allowed to be where that, remember what the probing sequence said over there, I always do it by multiples of H prime of K. If H prime of K is equal to 0, then there's no hopping happening. Our bunny's not going anywhere with those rocket-powered boots. Which, that isn't fun at all, right? We want to be friendly with our bunny, okay? So anyways, this is a good secondary hash function. But what we're going to do is I want to do an example just to illustrate how this works. So let's do an example. I'm going to make a hash table. I'm going to make it have 7 slots in it. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. It's going to have this table size of 7. Remember, 7's a prime number. And what I'm going to do is I'm going to use a primary hash function of H of K to be K mod 7. And the secondary hash function is going to be H prime of K, which is going to be equal to 5 minus K mod 5. So notice that Q, I've selected Q to be 5, which meets this definition here. So I must stress that if you set this up appropriately, you should be able to satisfy this property, no problems. So, anyways, let's talk about this. Okay, so now what we're going to do is I'm going to put some records in, and we'll see what happens. Now, for simplicity purposes, I'm just going to give the keys, just for the sake of time. So we're going to do 1, 8, 3, and 29. So when I go through each one of these, I have to apply the hash function. So I'm going to apply the hash function to each one of these. So if I apply H of 1, well, that's just 1, right? H of 8. Can somebody tell me what H of 8 would be? Remember, it's 8 mod 7. So what is it? What is it? It's 1, exactly. It's 1. Okay, H of 3 is easy, that's just 3. 29, that's 1 because it's 1 higher than 4 times 7. So, anyways, what we're going to do is we're going to be placing each one of these to start from the top all the way down into our hash table using double hashing. And I must stress that the same process is going to apply as we seen just a moment ago, except now I'm applying a new probing sequence. That's the only thing that's changed. So everything I said about lazy deletion, all of this is still in effect. Just the difference is now my hops are dictated by this secondary hash function, as we're going to see. So, anyways, I'm going to start off by just placing in this first one. Okay, just go right here, right? It's free to go in there just fine. So, there's no collisions or anything like that. So, let's see what happens when I try H of 8. So now notice that 8, it will hash to the position 1. So we're going to have a collision that happens right here. So that means I'm going to have to compute the secondary hash function. So let's try that out. Let's see what, sorry, let me write it down one lower. H prime of 8. H prime of 8, well, look at this. It is 5 minus 8 mod 3. 8 mod 3 is what? What is 8 mod 3? So what's 8 mod 3? Yeah, 8 mod 3. Sorry, 8 mod 5. 8 mod 5. Sorry, 8 mod 5. 8 mod 5. For some reason, I had in my head that it was 3. Yeah, it's 5. My apologies, everybody. It's 3, yes. For some reason, I read it off as a 3. I guess I was looking down here. Thank you. Thank you. I was like, what am I doing? But yeah. Oh, that's funny. That's funny. So, anyways, we know 8 mod 3 is, sorry, 8 mod 5 is 3. I'm guessing I'm thinking of the answer. I sort of gave it away. 8 mod 5 is 3. 5 minus 3 is 2, right? So, to do my probing sequence, I do 1 plus 2 mod 7, which this is 3 mod 7, which is just 3, right? So I'm just going to place 8 in the position 3. Then let's do h of 3. So let's figure out what h prime of 3 is. Well, I have 5 minus 3 mod 5, which this is just 3, right? 3 mod 5 is 3. I made sure I said 5 this time. Then we have 5 minus 3 is 2, right? Oh. Oh. So this is just an example. If I use a different prime number for the table size, like if it was, say, 11, I could use, for example, 7 instead of 5. This is just an example. So now notice that this is the same number here. So you know right away when I attempt to place 3, it's going to go right here and say, hey, look. So I start here, I get a collision, I attempt to apply it here, get another collision. So I know right away that I'm going to end up having to do, what am I at? I'm at position 3, right? So I'm going to have position 3, and I'm going to add 2 to that. Mod 7, which is just 5. So I'm going to make another hop of 2. Because remember, I go up by multiples of 2 now. So now instead of it just being one hop of 2, I'm going to take another hop of 2. That takes me to 5. So that just means I'm going to put 3 right here. And then lastly, I have h of 29. Let's see. So confused. Where did 8 go into position 3? Okay, so just remember, the whole idea was with the probing sequence. So it says 1, so I get 1 for the initial attempt. But remember, h of 1 is 1, so 1 is already here. So I get a collision. So that means I have to apply the secondary hash function. Remember, the probing sequence is I try h of k. If that fails, I go h of k plus h prime of k, mod m. If that fails, it's h of k plus 2 times h prime of k, mod m. And if that fails, it's h of k plus 3 times h prime of k, mod m. And you keep doing this over and over again, as per the same algorithms I gave you, except instead of going plus 1, you just apply h prime of k. Yes. Yeah, so now, let's see. We got 29. Now this is where it gets a little bit fun. So h prime of 29. So let's see. We have 29 mod 5. You know that's 1 less than 30. So you know it's going to probably be 4. Yeah, it'll be 4. Then you have 5 minus 4 is 1. Actually, let's work this one out together because I think it's important that you see this at least once. So if I do h prime of 29, well, that's going to be 5 minus 29 mod 5, I made sure to remember it's 5. 29 mod 5. Well, 25 is 5 times 5. 5 times 6 is 30, but that's 1 less than 30, so you know it's going to be 4 here. So you have 5 minus 4, which is just 1. So this is just going to be equal to 1. And now, all I do is I started in position 1. And now I'm just going to take 1 plus 1, because that's what h prime of 29 is, mod 7, which is going to be equal to 2. And you see right here, I can just put it right there. So this is just an example of me showing you how the probing sequence gets applied. It's a little bit more involved, but it's the exact same principle. The difference now is instead of it just being a cute little bunny that hops 1, 1, 1, 1, it's going to be now that the bunny has rocket boots that go and take the bunny from all the way from, say, one spot on this table all the way to the other side of the table if I run into enough collisions. So instead of it being 1, it's just one really big leap with rocket boots. I hope I didn't murder anybody's ears with that. So, anyways, so I must stress that get, put, and remove are all the exact same as I just discussed, except you apply the new probing sequence. So let me just make that remark. So I do have an example of what one of these would look like with the secondary hash function in place in the notes, like with put. So I show what put looks like in the notes. So get, put, and remove are all the same except the probing sequence. So everything I said about linear probing when it comes to complexity is the exact same here. So get, put, and remove are all the same except the probing sequence. That's it. It's really neat. So you might ask, Dan, I want to address one very important question. You know how I said that the table has to be prime? I think it's very important that I touch base with you on that issue. Because you might say, Dan, why do you have to make sure the table is a prime number? That surely seems kind of arbitrary, right? Because you've mentioned that it's kind of good practice to do that, but like, why do I have to do that here? So I want to do one more example just to really kind of hammer in this. But I also want to show you just why sometimes these number theoretic things, sometimes every once in a while, creak their head up when you start talking about hashing. So let's do another example. And I want to talk about why you would need to do this. So what if t sub 2 has some element in it? How would 29 store there? If there's something already there, you would just continue doing the probing sequence, right? That's it. That's all it is. So I want to address why must the table size m be prime? So I want to show you an example of why this is rather important for us. So I'm going to make a table. It's going to have 8 slots in it. Sorry, it's a little squeaky. 1, 2, 3, 4, 5, 6. That's a little crooked. It's sort of melted there. It's like a Tupperware that kind of went in the microwave a little too long. So I'm going to have the table have 8 slots. My hash function is going to be h of k. It's going to be k mod 8. And I'm going to select the following secondary hash function. I'm going to make it 7 minus k mod 7. So I've just selected a prime number, and it's less than the table size, so it's okay. The only thing that I've done that's a little different is now the table size is not a prime number. So I'm going to try putting in 3 records into this. Their keys are going to be 2, 6, and 10. So I'm going to apply the hash function to each one of these. 2, 6, and 10. Well, 2 mod 8 is just 2. 6 mod 8 is just 6. And I will mention that 10 mod 8 should be 2, right? So we have those, just so that we have an idea what's going to happen. So when I attempt to place this one in, so I use a put operation to place this in, okay, it tells me to go to put it in position 2, so it goes right there. I attempt to place 6 in there, and it tells me to put in position 6. Now let's attempt to place in the record with key 10. Now, this is why it's important, so watch this. Let's watch this. And I assure you, I'm not trying to mess with you. So I'm going to compute the secondary hash function. Remember, this tells me how much the offset, how far the bunny jumps. That's all it does. It's nothing too alien. It's just telling me how many hops, how long the hop is for the bunny. So instead of it just being 1, it's just this, whatever this value is. So I compute 7 minus 10 mod 7. This should be 3. So I have 7 minus 3, which this is equal to 4. So my hops are all going to be of size 4. And remember, my initial place I'm going to place. Yes. So keep in mind that now this secondary hash function operates like the size of my hops. So instead of it just being 1, it's 4 now. That's what I'm saying. So that's why we're going up by multiples of the secondary hash function. So notice here I would start off here because that's what h of 10 tells me to do. I check here first, and then what I'm going to do is I'm going to perform the hop, but the hop tells me to go 4. So I'm going to go, so I would check 2 plus 4 mod 8, which is, this is equal to 6, right? But there's something already in 6. So I make a hop, I hopped over here, but there's something already there. So I need to go 2 plus 2 times 4 mod 8. But 2 times 4 is 8. So 8 mod 8 is 0, but 2 mod 8 is just 2. So I end up with 2 again. So I'm going to perform a hop. I'm going to hop all the way back over here. And now I'm going to attempt this again. 3 times 4 mod 8. Well, 3 times 4 is 12, plus 2, that's 14. Well, if you think about it, that's just 2 less than 16, right? So you know it's going to be 6 again. So if I keep doing this over and over again, so notice I would hop over to 2, then I hop over to 6, then I hop over to 2. If I keep doing this over and over again, I'm just going to keep hopping back between 6 and 2, 6 and 2, 6 and 2, 6 and 2. So the record with key 10 never gets inserted. It never gets inserted. So now we're stuck, right? That's exactly it. So our poor bunny is stuck in the perpetual loop I was warning you about, except it's even worse than that because now the table's not even full, right? The probing sequences worked against us, but it's because of the table size. So we have a term for this from number theory, and I'm just going to tell you a little bit about that. So there's something that's really important in double hashing, is that because the numbers that come out of the secondary hash function are never 0, we need to make sure that whatever comes out of that secondary hash function, in relation to the table size, they're never divisible by each other. Except if it's 1. So the only multiplicative factor, or divisor, is allowed to be 1. We have a special term for this. In fact, there's a couple different ways, a couple different terms for this. So we say 2 integers two integers are relatively prime. Sometimes this is called coprime. Coprime if the only positive integer factors or divisors, whichever phrase you would like, factors, divisors, that divide both is 1. So just as an example, just to illustrate this idea, 3 and 8 are relatively prime. Because think of the divisors of 3. So think about it. So if I want to think about the numbers that divide into 3, there's really only 2 because 3 is a prime number, right? Its divisors, by definition, are 1 and 3, right? The divisors for 8, if I go running through them from smallest to largest, it's 1, 2, 4, and I think we also have 8, right? So obviously 8 divides into itself, right? So the one thing that's great about the way I've told you how to assign the table is that you notice that that value q and m, q is never bigger than m. So I make sure that the value that comes out of that never exceeds capital M. So we know that one of these is going to be a prime number that's going to be bigger than the other number when I actually start trying to add over in terms of sums. But I'm not going to prove this, but what we are doing here is that the size of the table, M, and h prime of k must be relatively prime. Now that's the reason why you couldn't, like in this example, that's not true. But I'm not going to prove this. So if it is the case that it is, though 8 isn't a prime number, we're talking about a definition called relatively prime. So relatively prime isn't the same as prime. It's a comparison between two numbers. Notice the ones in common here. So notice I look at the divisors of 8 and the divisors of 3. The only one it has in common is 1. So if it is the only one that is common amongst the two, we say it's relatively prime. So this is something that we require for our double hashing, is that m and h prime of k. Remember, this could be some output of the function. So I require that both of these are among each other relatively prime. But yeah, any two real prime numbers most certainly satisfy this definition, right? That's a wonderful observation. That's a very wonderful observation. Yep, that's essentially it, right? So as long as I can make sure that this number never gets big enough to be as big as this number, and keep in mind, sometimes prime numbers come out of this one, but this is most certainly a prime number, always. But it's never going to get as big as this number. So we know that this is going to be the case because this is a prime number. This, if I compare it against that, the number of factors is never going to get big enough to be as big as this number. But so that means that I'm not going to prove it for you, but I'll let you think about it, why this would be the case always. So I'll think about that afterwards because we got to stop right here. That's actually a wonderful question. One thing I want to quickly address before I leave is that I'm going to ask you to take a look. So I'm just going to ask you to take a look in the notes, look at revisiting the load factor. So in this, we address the question of performance. Which ones are appropriate for which load factors? So you're going to find that separate chaining tends to be the one that performs the greatest, because of course we use so much memory to do so. Then it's double hashing, and then linear probing is the one that's in last. So that being said, when we come back next time, we're going to start talking about a brand new topic. We're going to start talking about trees. So when we come back, we'll see all about whatever these tree things are called. So that being said, I'm going to let you go for tonight, and I'll say thank you very much, and have a beautiful day. I'll see you later.